All right, so this is problem R8-4. And so as we enter into November, getting closer to December, we're hitting the snow season. And so it's nice to have a problem that relates to real life. If you don't know what a gondola is, it's really a capsule that takes you from point A, the bottom of the mountain, to point B, to the summit / peak of the mountain, so that you can come down on a snowboard or a ski. And if you do, just be safe. Remember, don't try to fall around while you're in there because you could fall off. So make sure the doors are closed and be safe. So the question is asking, the gondola and the passenger have a weight of 1,500 pounds and center of gravity at G. The suspender arm, AE, where is the suspender arm? A. Ooh. Oh, so the suspender arms is referred to as the entire thing, A, all the way down D. And they're saying that you have an applied load of 1,500 pounds downwards. Okay. And the suspender arm has a square cross-sectional area of 1.5 by 1.5. So cross-section means that you do a cut. And what does that look like? Well, it looks like a rectangle. And it is 1.5 inch. 0.5 inch. And what's really cool is the moment of inertia, because you've got moment of inertia is equal to 112 BH cubed, and guess what? B and H are twins, and so therefore you've got 112 H to the 4th. How awesome is that? All right. So as we are carrying, well, that thing is just annoying. Anyways, okay. So here you again have a axial and bending. So we got to make sure that we understand what the axial and bending includes. So let's see. Determine the largest tensile stress developed in regions A, B, and D, C. Let's see. AB is right there. And D, C is right there. So this is going to be interesting because segment AB, actually segment AB is really simple, because if you were to take a section cut at AB, you'll find out that because the load is applied to the center of that segment AB, because you have no offset in distance, so you know that the stress is actually just equal to P over A. And A is referred to the area, which is 1.5 by 1.5. P is the load of 1,500. So that actually is pretty straightforward. And if you did that, since we kind of gave it out, it's 667 psi if you were to solve for it. Now, that's the easy part, right? And so the question is, as AB shifts over, oops, right, you introduce what we called a eccentricity, that's an E, And so we know whenever you do that, you've got a moment, right? Because you have a force times a distance, right? So your moment is equal to force times distance, and you know that the force is equal to the 1,500 pounds. And here the distance is unknown, but check it out. Looking over here, we know that that eccentric distance is 1.25. So then we know that the moment is equal to force, which is 1,500 pounds, times your distance of 1.25 feet. Make sure as you solve that you are consistent with units, right? Because your inertia will most likely come into inch to the fourth. It's standard practice to have it in that units in America. And so as we erase all this stuff and get it out of the way, okay, we know that the stress at B is equal to P divided by A. And then we have MC over I. Okay? So therefore, and then plus or minus, I'll kind of have you decide what that is. Because you are trying to find the worst case, so you gotta think about it. Now, if we were to look at that solid block again, right, we know that the stress diagram due to bending is going to look like that. And if we know that the axial diagram is that, the maximum would be this plus that. And so you would actually take that and it would kind of push it up that way, and it will take away from that. So that is going to be your stress max, if that all makes sense. Okay? All right, well, good luck. All right, so now we're moving on to problem 8-44, and it says determine the normal stress developed at point A and point B. Neglect the self-weight of the block. It just makes the calculation easier. And so we first need to find out where point A and B are. Okay, and so we zoom in. Oops. Point A and point B are located here. Now we know that we've got an eccentric loading here, and so we would then have a moment. So I think really the easiest way is to find out what the moment is and really determine what it is first. And so if we define a axis here and axis here, maybe that needs to be erased because it's it's not really all that growing that well, but really if we were to redraw it, right, it's point A, it's point B, that's point D, so that's got to be point C, and it's saying that at this corner right here you've got a 12 kip being applied into the page, and at this corner right here you have a 6 kips of load being applied again into the page. And so if we say that that's the x-axis and that's a y-axis, we know, right, that we have a moment, that the moment due to this load causes a rotation up there, and the moment that's created due to that load causes a moment there. Okay, so here the super confusing portion is really making sure that you understand the moment of inertia as it relates to the axis. And so that's probably the most confusing portion when you're solving for these things, because besides that, it's pretty self-explanatory, right? So here you would solve for the moment, and so you would have a moment about one axis, a moment about another axis, and keep in mind that we have an axial load, right? So what is the formula that we would be using? So we would be saying that the formula would be that sigma, or stress, is equal to force over area minus or plus, you have to determine which one based on the loading. You've got moment due to a certain axis over the inertia and c, and then plus or minus, you have to determine the direction, moment plus c over y. And so to kind of identify this in more detail, one would be x, 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 and the other one would be y, y, y. And the question is, what is f? And so if we scoot over to the side, is f 6 kips or 12 kips? It's actually the summation of that load that's acting on that plane, which is into the page, correct? So therefore, F is actually 6 kips plus the 12 kips, and the area is referring to the cross-sectional area that you're looking at, and this is defined as 3 inches, and this dimension of 6 inches. So hopefully that helps. And let's see. And so I think the question is asking you to do it at point A and point B. So depending on where you are, this is really what's going to throw you off. So you got to really think about how it applies at that different location. Okay? All right, guys, good luck on this one. All right, so we're moving on to the next problem, which is 8-22. Here, a steel bracket is used to connect two ends of two cables. If the allowable normal stress of steel is 30 kSi, determine the largest tensile force P that can be applied to the cables. Assume that the bracket is a rod having a diameter of 1.5 inches. Okay. So here you have, again, a combined axial and bending. And really, let's kind of take a look and understand the structural analysis of this. And so when you're doing this, you would naturally cut this section right here And at this point, you'll have a normal force that's being pulled, and you'll have a moment, right? So here, your load that's being applied is your P load, and you know that your P times that distance of. Now, keep in mind that you're looking at the center of that member, and therefore, if you know that that is 1.75, right, that you would have to, or sorry, 1.5, you know that to the center line of that member, to that point, is really equal to, or actually equal to, 4.75 inches, right? So here again, you're given some hint on, and you're being asked to solve what the P load is. So we know, different from the previous problem, right, which was problem 7-19, that in 7-19 they're saying that the stress would equal to 0 because that is what you're solving for. Here they're saying that your allowable stress is equal to 30 KSI. And then that's also relates to your max stress that you'll ever achieve. And so we know that the formula for stress for both axial and bending was equal to P over A plus MC over I, right? And then the C is referring to the bracket. And so the bracket, let's see, has a dimension of 1.5 inches. So you know that C is half of that depth. So that's equal to 0.75 inches. Okay. And you know through the formulas, the inertia of this bracket, if I was to take a section cut, right over there, it would have that, and you know that the diameter is equal to 1.5, right? And then from there you can find out what your inertia is. We know that the moment is equal to force times distance, right? And we know that the force is P because that's your load that's being pulled. Multiply by the distance. So different from the previous problem, which you were solving for the distance. Here, you know what the distance is because it's 4.75 inches. Oops, interesting. Okay, so I think the combination of that would allow you to start solving for that. Good evening, everybody. So I will not be able to make it to lecture for both Monday and Wednesday. And so what I've decided to do is actually assist in the homework process. So here, what I'm going to do is really get some hints on how to solve it and what to think about, and not answer it with a numerical problem, but enough information to really get you started. So problem 8-19, it is a combined loading problem, refers to the chapter 8 of Hibbler. And so here, what we'd like to do is, we know that when we look at this loading right here, because of this offset that is given, right? That would then create a moment, right? That looks like that. And so I believe the question is asking for is determine the maximum distance d is, so d is actually what you're solving for, at which a force P can be applied so it produces no compressive stress on the plane of section AA. The plate has a thickness of 20 millimeters and P acts at the center line of this thickness. And so what we know is that we are solving for distance d. We also know that we have an axial load that's being applied, right? So the two formulas that we will be using are stress is equal to N over A, or N is really referred to as your P load, minus, due to the offset, you have a MC over I. And we all know that because of this, that the moment of inertia of that section would be 112 BH cubed. Right? And so from there, what you're solving for is what is the load that produces the moment or the offset distance. And so from here, we know that all right, sorry about that. I had to just pause the video to take care of something. Anyways, I don't really quite remember where I left off, but it doesn't really matter. And so when we look at it, we also have to look at what the moment is. We know that the formula for moment is force, or P, times your distance, right? And so we're solving for that distance. Now, we got to make sure that we don't get confused between this D and the other D, so I'm going to label that as D prime. And really, D prime would be measured from the center line, so that actually would end up turning into D minus 0.1 meters, because you're measuring from the center line, and that distance is 0.1, so you want to know what that distance is. And you can also take it at a different point of reference. You get the same answer, so it really does not matter. Anyhow, the question is also asking that there's no compression in this problem. So you have an axial tension and you have a bending, so we have to look at it in terms of how the stress looks like. We can all agree that the stress for an axial load would equal to this way. And so we would also have a bending moment. Right? Looking like this. And so if we say that this is tension, that's compression, it's saying that it doesn't want any compression, so that means that the tension has to overcome the compression. And so that's the key. And so that's what you're solving for. And also to clarify here, A as the problem has stated, is 0.2 meters. And that width is stated as 0.02 meters. So you've got most of the stuff. You can solve for area, right? And so that's really what you're solving for. And we know that C, right, is half this distance. So it's going to be 0.1 meters. And I think that's enough to get you started on this problem.